Welcome. I'm Mike, a Googler, a statistician, and I'm passionate about learning and sharing. Today, I'm a friend and I welcome you into my office. We are in a series of videos that are covering a GitHub repository that contains end-to-end workflows using Vertex AI to do machine learning operations. These videos' goals are to go from the entire range of the process, from taking data, preparing data, training a model, evaluating that model, deploying that model, getting explanations and predictions from that model, monitoring models, you name it. We're going to cover all kinds of things in this series. These are built from my experiences working with customers, with friends, with colleagues, my own curiosities throughout my career. And in each one of these, we're looking at a different way of doing things, a unique fingerprint. Some of them are related. You are in a series right now that I call the O2 series. Let's bring up a screen that shows the repository. These notebooks have labels. We covered 0.0 setting up the environment. If you want to follow along and run these with me, make sure you've seen that video. 0.1 video, we built the data set that we're using throughout this. Then you can skip to any of the O2. You've ended up in O2C, which is the version where we're going to use AutoML. Don't stop yet. Don't click away. AutoML to build a model, train a model. We're going to do it as part of a pipeline. Now, what is a pipeline? A pipeline is this ability to put multiple parts of the machine learning operation process together in a graph, a sequence of, it can have branches, but it's a DAG if you use that terminology. The ability to put these pieces together and launch them as one job. I view it as a people mover. You get to the airport, you got your suitcase, you got your family, and you're trying to all stay together, but you're tired. Put them all together in one place and let them move forward together. And you could repeatedly do that in the case of machine learning with pipelines. The analogy might make a little more sense as we get deeper into this. From the repository here, if you aren't following along or running at the same time, you can just click the particular notebook and follow along there as we go. Everything we do is basically going to be running this notebook and talking about the decisions I made when I built this notebook. To kind of showcase what's happening here, I like this graph. Let's zoom into it. This series of videos, the O2 series, these three, A, B, and C for O2, we are in the deciding you want to code. We're going to use a Vertex AI Workbench, which is a Jupyter Lab environment, a Jupyter Hub. It hosts Jupyter notebooks, the ones in this repository. Okay, so that brings us to here. And we want to use Python since we're there. We could use the Vertex AI client itself called AI Platform to interact with Vertex components. We did that in the O2B video. But you're in the O2C where we're going to use a Vertex AI pipeline to build components, little compartments, to do each part of this job and connect them and let them share information, hand information off. It's a very simple one in this case. To make this be bottled up and be able to rerun. Some of the things I love about pipelines we're going to talk to as we get further along here. All right, so let's jump in. We want to get to our notebook. So what we did in the previous videos is we went to Google Cloud. We came to Vertex AI. Under Workbenches, we've opened up a user-managed notebook. Once we get that running, we have a Jupyter Lab. And here we are in our Jupyter Lab. You see I have the O2A and O2B notebooks already open because I'm filming these videos at the same time. Let's open O2C. Okay, so at the top you see the video that you're watching right now. That is a link to it. Under here, we get the steps. Now the first is what pieces of Vertex are we going to use? A little graph that shows that. We start with a notebook. We are going to orchestrate a pipeline. That pipeline is going to bottle up creating a data set from a BigQuery table. It is going to, in sequence, create an AutoML model using that data set. It'll be a tabular model because our data set has rows and columns. It'll then create an endpoint and deploy our model to that endpoint. And then once that's done, we can interact with that final asset, that model resting at an endpoint that we can ping and say, give me a prediction. We will even give some bonus content. We'll ask that endpoint for explanations, and we'll talk more about what those are. That's great bonus content for this one. As far as visually, what does it look like? Well, we went from notebooks. This is where we're at right here. And then this notebook is going to interact with pipelines, which will interact with a bunch of services. And then finally, the notebook will interact with predictions. To get going, the one parameter I need to change is the project name. Just like you, I've downloaded or cloned this repository. I have to change the name for the current project, StatMike Demo 3. We're going to use US Central 1. Our data set name is fraud. Our notebook here is O2C. I use that to label assets as we go, so I can distinguish which notebook is creating which things. We are going to need to provide a compute type for our endpoint. So I go ahead and parameterize that and give it in1 standard 4 here. Model training, we're going to store a little bit of information in variables that we can use lower down. One, which column is our target? Remember, we have that fraud data set. Rows are transactions. Columns, the features, they don't necessarily make sense to us because to kind of de-identify things, they've run PCA analysis. They've re-parameterized that into a smaller dimension. It gives us columns V1 to V28. We're feeding those to our model. The column that they give us in addition is the one that labels it. Fraud 1, not fraud 0. And that column is called class. And I store that here as the var target. I want to be able to tell later on in my code columns to ignore. The one that I'm going to give it here is transaction ID. Remember, I created a unique ID for each row because it didn't have a way to identify rows. That's uninformative to a model. If you include transaction ID and it somehow helps predict, well, it's going to be useless for future predictions because you're never going to get the same transaction ID again. We're going to load some packages, primarily the one that allows me to interact with AI platform, KFP, Kubeflow Pipelines. That is the high-level API that we're going to use to build the components and put them together in a pipeline to feed Vertex AI's pipeline service. Later on in videos, when we're using TensorFlow, we'll even talk about you can use TFX, TensorFlow Extended, to do that. Today, we're using KFP. We're going to load Kubeflow pipelines use components, these little objects that allow you to interact. One, they create a containered space that gives it compute, but they also have capabilities with inputs and outputs and what they do inside. You can build custom ones quite easily. There are some pre-built ones for Vertex AI services, like the data set in the AutoML model. We're going to use those, and we load those with Google Cloud Pipeline components. Create a BigQuery client. All right, let's go ahead and run these. We want to create a initialization for AI platform. We don't want to keep telling every service what the project ID is, what the location is, so we can initialize that, create a BigQuery client. Parameters, I'm going to create a timestamp of right now, use that to label things to distinguish in case I run this notebook again. I'm going to use Google Cloud Storage Bucket as it's named the same as my projects. I create a redundant name here. URI is the location of where I want to store assets. I'm creating a model with this pipeline. I need to tell it where to store that asset to load it in Vertex. So I'm going to go to the bucket. I've got a folder fraud, the data name. Under there's models, and I'm going to create a subfolder there for this notebook. I'm also going to create a local directory for the notebook assets before I move them over to Google Cloud Storage. So I see I just created a variable that will name that. Let's also, to run a pipeline, we need to know the service account that's being used in Vertex. Now, a cool part, since I'm using a user-managed notebook that's already running in Vertex AI, this notebook's running with the service account. So I can actually go to the environment parameters and extract that information right into my notebook here. That's what this cell is doing. If you want to study that, it's running a gcloud command at the command line to get configuration for the project. It's extracting the account that's running it, storing that value in a variable called service account here in Python. Printed it out. Now I'm creating that local folder I was talking about. There's O2C. It's empty right now. We'll create some stuff to put in there. Next thing, we're going to define the pipeline and run it. So as we go into this, we have to consider a few different things. There's the parts of AutoML, like building the model. We're going to talk about those. If you watch the other O2 videos, A and B, you're going to hear me talk about some of the same things again. And since we're here in Kubeflow and talking about pipelines, we should talk a little bit about that. Before we do it, let's first talk about, well, we're building a tabular data set version of AutoML. What else is AutoML capable of? So let's start with that.
Hi, Mike. What types of models can I train with AutoML?
This is a great question because AutoML is this service where you feed it data and it trains a model and gives you that model. What does it do in the middle? It does feature engineering for you. It will do things like, hey, this is like a categorical variable. Let me twist that out, transform it, and make each category its own column, and 1 or 0, is it that category or not? It sees numeric columns and says, hey, maybe I should standardize those. So let's calculate the mean, subtract it, and divide by the standard deviation of that column. It'll see things like dates, and it'll extract parts of dates and time to use for that. It can see text, and it can extract information from text as well. What are the types of models that you can build with this is a good piece of this question. So let's share a screen and let's walk through and talk about that a little bit. So I've opened up the documentation here for AutoML model types. What I like about this service is you're probably thinking, depending on what your background is, like, why wouldn't I just build my own custom model? The rest of the videos in this series are all about custom models. Here, we're talking about AutoML, which I love because if nothing else, it builds a great baseline model that you're going to try to beat. I find that frequently I can't beat it, and that's a good thing. It is limited in what types of models it can build. It's vast, so let's talk about what that vastness is. You can give it image data. So if you've got a bucket in Google Cloud Storage full of images, that could be your data set. And you can train it to classify those images. So you've got some labeled images. These images have cats or dogs or a particular breed of cat or dog. And you can train that model to look at images and figure out what about the images says that it is that thing. You can detect objects, like say which images are, what is in this image. And it can come back and give you a list like, hey, we see a dog in there, we see a cat, we see flowers. You could train it to do that detection task. Today we're using this tabular data, transactions for a credit card, particular rows are labeled as fraud or not fraud. So in the world of tabular data, you're going to have 3 types of models that you can train with AutoML. They are supervised. The one we're going to focus on today is classification. That means it has classes, small, medium, large, yes or no, fraud, no fraud. We'd even call that positive, it is fraud, negative, it's not fraud. You could also have a regression type model where the target that you're trying to predict is more of a numeric value. It could be the size of something, the age of something, the account balance, things like that. Very similar to a regression model, you could have a forecasting model, which is a little different in that it has groupings of rows. And in those groupings, they have a natural order that is time. It could be measurements on days or weeks or months or quarters or years. And that target, that column that you're trying to not predict in this case, but forecast, is to look at that target over that time space and then see where you think it would be 1 space into the future and 2 time points in the future and then 3. And that would be a forecasting model. That's not our type today though. You can also do text data where you can do similar to an image. You can say, well, let's classify it, single or multi-class, what is in this text or what is this text about? Is this a An essay is this a text document. You could do entity extraction, where you try to extract information from the text, labeled information about that text, like not cat dog, but is this text about taxes, or is it about school essays? You could take the sentiment of text. You could come back and say, is this positive or negative? Very helpful information. Maybe you're even just trying to route information and say, well, if people are positive about something, let's send it this way, and negative this other way. Video, similar to images, but now they're moving. So you could have segments, a single frame of a video, or a segment of a video, or the whole video, and you could classify those pieces. You could detect objects in those pieces, or you could look at action, like watching a ball move in a sporting event, or a hockey puck kind of thing, or a golf swing. Coming back from that, let's jump back to our code and take a look at what's happening next in it. All right, so what we have is a pipeline. What a pipeline, you get these decorator things from KFP, where you define KFP Kubeflow pipelines. We've loaded that client, and it's higher level than the Python AI platform SDK, meaning what I mean by higher level is we are going to call the same things we did in the O2B video, but we're going to call them as components inside this pipeline from something that's actually going to pass parameters to those same pieces. But they're kind of smaller, they're more summarized. Now, in that previous video and in this one, what we're doing is we're going to define our pipeline with inputs. Okay, project, dataset name, display names, that machine type used for the endpoint. Our data is coming from BigQuery, so we have to tell it the path to the data set. The variables that we want to include as the target, the ones we want to omit, any labels we want to use, these are all coming into the pipeline to be used. Now, in the pipeline, we have components. These components are going to run in their own container. That's a pretty magnificent thing. Like, we're not building infrastructure here. We're not building a GKE cluster and giving it size and load balancers and telling it stuff. We're just using Python to say machine learning has tasks. Tasks are in components. We're going to connect these components, and we're going to let Vertex AI go create an infrastructure and run this for us. In this demo, I don't need to do this, but you could even specify like how much GPU or CPU these components need, or what version of Python they need, and you could custom, that's future videos for custom training. Here, the first component, we need to create a data set in Vertex AI. That's just this concept of Vertex linking to a data source in Google Cloud Storage or in BigQuery, our case BigQuery. This component is, remember we loaded Vertex AI's components. The particular one is a tabular dataset create operation. We tell it what project in Google Cloud, that's StatMike Demo 3. We give it a display name. We tell it to use BQ as the source, and we give it the variable BQ source into the pipeline to use. And we're going to label the asset that it creates. Now, when that is running, inside the pipeline, we're going to do a little housekeeping. We're going to go to BigQuery, and we're going to create a client for BigQuery. We're going to query the information schema to get all the column names from our data set. And then we're going to doctor up the list of column names a bit. We're going to omit any variables above that we listed as omit. That's transaction ID. We're going to omit the class, the target variable. We don't want to give the training the target to train with, or it'll be perfect and perfectly bad at future predictions. And we can also take out the splits column, because you don't need that to train. You just need that to split the data. We'll use it separately later. So we doctor up that list, and then we build a list of features from that list of column names. And we're going to make a dictionary from that we're going to pass into the next component. This component is going to build an AutoML tabular training job. Now the inputs, project again, display name. We need to tell it information specific to building a tabular training job with AutoML. The model type, we just talked about these. Ours is classification. Fraud, not fraud, is our target. Optimization objective. Good place to pause here. So let's do a little Q&A. If you've watched the other two videos, you've heard this, but that is okay. We'll see if I get better at explaining it. A good question for this is...
Hi Mike, what optimization objective should I choose?
Okay, so we have this classification model with fraud, not fraud. There's a default when you say classification and it sees only two classes. That default is to optimize the loss function based on the area under what is called a receiver operating curve. The y-axis of this curve is the number of true positives. You want that to be high, like it was fraud and the model calls it fraud. That's a good thing. The x-axis is it's a false positive. It called something fraud that wasn't fraud. You want that to be very low. That would normally be a perfectly fine way to optimize and build this model. But we could do better. We have a little extra piece of information we identified in the the 0-1 video where we looked at the data source. We know that fraud's only like 400 and something cases out of 250,000. That's highly imbalanced between those classes. For that, we want to use something different, and that is the area under the PRC, precision recall curve. The y-axis of this is precision. Precision is the ability to correctly predict positive fraud. So it's a fraction. Top is true positive. I labeled fraud that was fraud. And the bottom is that same number plus penalty, some mistakes. And that is going to be false positives. I called not fraud a fraud. You don't want many of those or you're not very precise. So that part, the x-axis of the precision recall curve is kind of the same, but a little different. It starts with the same thing. It's the ability to recall positive values, fraudulent values. Well, your training data had these. It didn't have many of them, 400 and something out of 250,000. True positives, the ability to label those correctly, divided by those plus a penalty, which is a little different, and that is false negatives. It called a fraudulent value not fraud. You don't want many of those either. We're going to pick that optimization objective. Now, what other ones are available? If we have more than two classes, the default would have been log loss, which kind of balances the different classes. If you had a specific field that you're in where it's important that precision not be below a certain level or recall not be below a certain level, you could fix those and optimize against the opposite ones. You could fix recall at, say, 95 and optimize precision, or you could fix precision at, say, 99 and optimize recall. What we're going to do is switch back to the code and look at our choice, which is maximizing the area under the precision recall curve. Now, the next is the budget. We want to tell it how many hours to run. This is how many hours it at most will try to build models. It'll build multiple types. It'll look at ensembles of them. It'll pursue paths that are giving better results. This is millinode hours, 1,000. So 1,000 of these is 1 hour. So we want to give it 1 hour to go at most. Disable early stopping is a double negative. The ability to stop early means, hey, it kind of sees that it can't get better. It's been trying a while, so maybe stop rather than keep going. We want to say, yeah, it is okay to stop early, so false to disabling it. Column spec, that's that list of features we created back here in the main pipe. Data set is the output of the previous component, which was called dataset outputs, dataset value. That's passing values between components. Target column is the variable target. Predefined split column, we created that. We've already, in our data source, created a column called splits that has test about 80%, validation about 10, and validation. What was my third one? Training about 80%, test about 10, validation about 10. So we don't need to tell this to do that for us. We just give it the column name. And finally, I'm going to label my assets that this creates. When that's done, we have an endpoint creation. This container is going to run, and it's going to take as an input the project, the display name, labels. Now this is a blank endpoint. We're then going to create a model deployment component that is going to take the endpoint and the model created both as inputs and is going to deploy the model to the endpoint. This is where we give it the compute type, deployment machine, the N1 standard 4 that we did above. And we're going to tell it to route all traffic to this model because it's the first model going to the endpoint. Endpoints can scale. We get some parameters for that, like minimum replica count. We want it to be on and ready to score. If you were getting lots of prediction requests per second or millisecond, that one N1 standard 4 might not be able to serve all those. So we could make max higher and give it the ability to crank up more machines as prediction requests come up and then relax those as prediction requests go down. And for our demo, we're going to keep it at 1. It's just me using it for this demo. All of this is bottled into this one thing, a pipeline. We're going to run that. Now, the next thing you do once you've built that Python piece is you compile it using Kubeflow pipelines. And compiling it means it creates a file that you can use that can be interpreted by the infrastructure to run it. That file is going to get stored in our local directory as a JSON file. We can hit run there. Get a little warning about a future piece. Kubeflow pipelines is being very actively developed, so you might occasionally see that. It's worth looking at. Under O2C, I see that JSON file, and if I were to open it, I get this great representation of all the things I just created that makes it easy for the infrastructure to interpret what we're trying to do. All right. Now I need to move that from my environment here in the notebook over to Google Cloud in my storage bucket. Remember, I created a folder for it before. We're going to use the gsutil command line copy command to move it from the local file to a file with the same name out in the bucket. Now, once it's out there, I can come back to the Vertex AI client, AI platform, and I can create a pipeline job. And it has very few inputs. I need to give it a display name. I need to give it a path to the file we just created. I need to give it a root where it can store stuff. I'm going to just make that the same folder out there. And I give it the optional parameter labels so I can see what it's created versus my other notebooks. All right, let's hit run on that. I can even ask for a response for running that with my service account. And we know that's going to run for at least an hour, probably a little longer because there's some pre-task and post-task that it does around that hour. So at this point, I can go over to the console. I can go to training jobs, and it might be too early to see a O2C training job running, but under pipelines, I'll see my pipe running. I can click the pipeline and I can see, hey, it's already working on the tabular data set. Hasn't started the downstream tasks that the outputs feed into. But creating an endpoint, that was independent because you don't feed it anything. It's already started doing that. Now, once it's done creating the data set, it'll trigger creating the training job. And once the training job and the endpoint are done, all the inputs for deploying the model are available and it'll run that component. Again, we didn't have to build an infrastructure that could containerize these and separate them and let them run and figure out the order. That little piece of code we just wrote built the people mover that made all of this possible. It's sitting here running, and if we needed to retrain this model in a few weeks or a day or based on monitoring predictions or the input data, that would be very easy to automate. We just rerun this pipeline and know that it would do all of these same steps. We could even add in steps that compare it to the previous model to see if it's better and then replace it. Right now, if I come back over to training jobs, eventually this will start an O2C job, and we know that's going to run at least an hour. So what we're going to do is go back to our title screen. I'm going to pause here, and I'll come back once that's done running. We'll review what it did. And we're back, and it looks like our our pipeline is done. Let's take a look at that. So sharing the screen here. What we see is that the pipeline we're looking at shows succeeded. If we go back into our code, we ran this, and it continued to poll and say pipeline state running, running, running. And once it was done, that finished up. That means we can review our pipeline. Now, my favorite way to review the pipeline is in the interface here. We're going to go back to the code and use the result of our pipeline. But when I click into the pipeline here, which we did earlier, we saw things had started running. Now we see the entire pipeline is complete. That means we kicked it off by creating the tabular data set, which was the link to BigQuery. Then that was going to trigger a training job. Independent of that process, we had an endpoint being created. And once the training job was done, it was deployed to that endpoint. We can do a few things here. We can expand artifacts. And we can say, hey, the dataset created a dataset. If I click that, it actually gives me a link. And if I click this link, looking at it, it actually just takes me over here to datasets and shows me the O2C dataset. Now, if you've watched O2A, which was point and click, create a data set, or O2B, which was code using a client to create the data set, you see that it gives you the exact same outcome, which is this connection to a data source. What's great about the pipeline is I didn't have to then wait and run the next cell or wait and then click the next activity. It actually jumped ahead. Like, you've watched the O2A and O2B videos. There's this part of the process where you deploy. That comes after it's done training. Those are already done. And even better is when you watch the O2B video in code, you first see me create an endpoint and then deploy the model to the endpoint. Well, here the endpoint was created in parallel with the model being trained, and it was sitting there waiting for it to be done and then deployed. So by creating a pipeline, all those independent operations are discoverable in this graph called a DAG, if you want to be very technical, that knows dependence and handoffs so that it can be optimal. And each part's in a compartment and it's operating. If I click into these compartments, I even get the information about them, like, hey, this is the name and the value and the region and which project it's in and the labels that you've given it. It tells me, hey, this took 2 minutes and 53 seconds to create. Deploying the model, that took 20 minutes. Creating the training job, that took 1 hour and 58 minutes. So it was longer than the hour we gave it because it has some extra work to do to prep and to create the model once it's finished. I see the timings of those. That could be very valuable information if I'm backtracking, but even better if I rerun this pipeline, I get the same assets, the same information for the same data set over time, different creations of information. You can make these graphs as complex as needed for your workflow. These are going to become a big part of future videos where we look at much more complex workflows. Pipelines really just bring all the chaos into order for us. I like to call them the people movers for a reason. It's like you package everything up, and once you get it on the people mover, it takes it to its destination, the other end, while you just restfully wait around for it. If we now want to use this model, in the other videos there was that pause where I went back to the title screen and we came back after deployment. Well, this is already deployed. I can go to endpoints, and I will see under O2C, there's already the model deployed. We can now use this model. Now, what do we mean by use model? Hey, we have a new transaction, and we want to pass it to the model at that endpoint and let it respond with a grade, fraud, not fraud. Let's do that. So let's go back to our code, and we're going to take it from multiple approaches. First, there's actually this one additional step here where I go to the pipeline and I get information about it. If we run that, we see, hey, in the pipelines within Vertex AI platform, here's the pipeline name, here's what it was run as, and here's information about it. We've already gone over and clicked. We know it exists. I want to use that endpoint. So first we need some data to send to it. Now a great source, in our case, we don't have new transactions. We have that original data set that we used to train the model. But I can go to that data set in BigQuery, and I can bring a subset of the records back into Python here to use. I'm going to create a data frame called pred for predictions. I'm going to go to BigQuery, and I'm going to select everything from the fraud dataset, fraud_prepped, that file we use for training, where it's test data that was left out of training. I even want to go ahead and subset a little bit further and say, and class equal 1. I want to make sure I'm grading a fraud record, because those are the ones that we're most interested in. And we also saw that's kind of the weak point of the model. It's great at calling not fraud, but fraud, it misses some. So maybe we'll get lucky and pass it one that isn't fraud. Let's limit it to 10 responses and bring it back. And let's take a look at those. What we see here is the first 4 rows of that. It has all the columns. It also has, since we're using that prep data set, it has the splits column. We know that's test because we subsetted the test. We know these are class equal 1. It has the transaction ID. We need to clean this up a little bit before we pass it over to the endpoint. The endpoint only needs what was used to build the model. We don't need splits because that was just partitioning the data for training. We don't need transaction ID because we didn't use that to train. We don't even need the class variable because that's what we want it to give us back as a predicted class variable. So we're going to use the variables we created up at the top of the code right here to clean that up. We're going to say a new ob is going to be the first record there. Let's even have some fun. Let's make it the 4th record there. And we're going to subset it to remove a few columns. We're going to remove the splits column. We're going to remove the target column that's stored in var targets. That's the class column labeled class. We're going to remove anything we put in var omit up at the top, which was just transaction ID in our case. And we're going to bring that list of columns back in their one row of data, row number 5, which is index 4 here. We're going to store it in this new ob. All right, we could even take a look at that real quick. Let's add a cell here, type new ob. What we see is, hey, look, there's a dictionary of just, variable value down the list. Now, what I learned from trial and error is AutoML took that time variable, which was actually number of seconds since a time point, if we go back to original source, and it turned that into a string to make it useful. So I'm going to reformat that variable as a string because the prediction endpoint's expecting that. And I'm going to prepare 2 more pieces, the 2 things that the prediction endpoint wants, instances and parameters. Now, parameters in this case, we can make empty because our instances have the parameter as a key value pair. I am going to create these, and then the easiest way to understand what happened with this JSON formatted version of new ob is to take a look. So we'll insert a new cell and just look at instances. What we see is this is a structured version of that transaction that is formatted in a special way that makes the endpoint be able to easily read it and understand it. And that structured value is this idea of a field named amount has a numeric value of 1. A field named time has a string value of 14073, etc. and etc. So we pass that specially formatted version of our new transaction into, first we'll use Python because we're in a notebook and it's using a Python runtime. We're going to go to that Vertex client called AI platform. We're going to go to the endpoint. We're going to list the endpoints. So well, there's multiple endpoints over there. We've run notebook O2A and O2B already. And once we do that, we can then pick one of those endpoints to get our prediction from. So we're going to do that. And we pick that and we get the O2C fraud. That's this notebook's endpoint. And then we're going to create, now I'll pause there for a second. In the O2B notebook, we created the endpoint in the notebook. So we were able to just use the response from it. In this case, we ran a pipeline which created the endpoint outside of the notebook. So I had to do this step to go list and return the notebooks that have the right name. I passed it the name I was expecting. And then I was able to take that and make a prediction against that specific one. So that's why this is a little different than the O2B network. So I had to go find the one created by the pipeline outside. What we're going to do now is send our record over and get a response that's our prediction. This is what we've done this whole process for. The moment you can feel it in action. So we get a prediction by going to the endpoint, dot predict, ask for a prediction, send it those two things we created, instances and parameters. And immediately we get back scores of 0.05 and 0.949. And those are probabilities of being a 0 or a 1. How do we know that? Well, in classes, it's 0 and 1. So these follow the same order. And we know that 0.5 is very, very low, so it's unlikely to be a 0. And 0.949 is very, very high. And it's saying basically we believe this is fraud with a lot of confidence. It used this particular deployed model ID. Remember, the endpoint could have multiple with a traffic split. This would tell us which model received this request. And explanations of none. We'll talk about explanations in a second here. All right, if I wanted to write a little Python to say, hey, go find the highest score, its index, and then go to the classes and pick the value with that highest score, I'd do this piece, and it would immediately grade it as a 1. I can imagine building my application. I receive the new transaction, I bottle it up, I send it over, I get it back, I run this Python, and I immediately know this is fraud. Route it to someone to go intercept, stop it from being paid, and act on it. Now, other ways you might do that. Maybe you're building an application and it isn't using Python. The next is going to do the same thing using REST. Now, the first thing I do when I use REST here is instead of a Python object, I'm actually going to write this to JSON in a file called request.json. So when I run this little row, it goes over here in my temp folder, O2C, and it creates this request.json created just seconds ago. And I open it up and I see it's just a really pretty version of that information to pass to the endpoint. All the variable value pairs. Now back in my code, I pass that file through a curl command. Now the exclamation part says, hey, I'm in Python in a Jupyter notebook, get down to the command line and then run curl. And post, authorization uses Google's CLI called gcloud to get my local authorization. Because I'm already in the project, I can just use that authorization to do the request. And then send that JSON file to the endpoint. And I parameterized it. The region's in a parameter and the endpoint name is in a parameter. So I pass those in, and I immediately get back a formatted version with the same info, the same values for scores, classes, tells me deployed model ID, even the original model that became that deployed model ID. So I get the same thing back. So maybe I'm working on building an application anywhere in any language. I could natively just use REST to route data to the endpoint and get back that set of info. Similarly, if I'm working in Google Cloud, a common tool is our command line tool we've already mentioned briefly is the gcloud command. It also has the facility to be able to go to an endpoint, give it a JSON file, and get back a prediction. And so that's what we're going to do here. Go down to the command line, run gcloud for AI platform, an endpoint, get a prediction, pass it the JSON. Let's hit run on that. And we get back this nice, simple little dictionary that tells us, hey, classes are 0 and 1. Those have scores of 0.5 and 9.4. You would pick 1. Now, Another thing you might do instead of online is you might bottle up all the transactions for an hour or a day and then try to score them all at night and then pick out the fraudulent ones and put them on somebody's notebook or dashboard. Maybe you're using, Looker from Google Cloud to have a dashboard for, people who are doing fraud detection. If you were doing it that way instead of in real time, you might run a batch prediction job. Now, back in the O2A video, we ran one of these where we basically pointed it to a data source with all the transactions and gave it a place to drop off all the scored transactions and let it run as an asynchronous job, just running on the side. Now, back in the console, those can be created and they show up right here under batch predictions in Vertex AI. You could go create here and even though we created this in Python, it's available here. You could pick the model O2C and give it source and destination and set it running. If you wanted to do that in code, because you're automating things, that's a great reason to do it. Right here under this cell, we see the code to do this. We would create a batch by using the client to create a batch prediction job, hit create, and we'd pass it the name, the model, the endpoint, source, destination formats, and some other parameters. And when we set it running, it would get going. If you want to see what that looks like, it's going to be essentially what we just did above for online for predictions for every row stored in a table in BigQuery at our destination. It'll prefix the table name with the word prediction, and it'll have them just sitting there waiting for you when it's finished. You could then have a workflow that's picking those up and acting on those elsewhere in your Google Cloud infrastructure. I'm going to pass on that for right now and take us to the bonus content, my favorite part of this. So an AutoML model, even our custom models in later videos, you can enable them for what's called explanations. Today, we're going to get explanations from this model. Before we do that, let's do a little Q&A to understand what these are.
Hi, Mike. What are explanations?
So my background as a statistician, I was trained on building these highly inferential models where each parameter was handpicked and included in a model. Maybe it was the interaction between multiple parameters, and you had these coefficients, these betas for these, where you would interpret those for scientific reason. In my world, we did clinical trials, and we would use these parameters to try to understand the impact of maybe drug A versus drug B. And maybe showing one drug's more effective than another. We might interact it with patient characteristics like age and gender or baseline value of, say, blood pressure. In the world of neural nets and more modern models, you have so many parameters that this is an infeasible technique. So very crafty ways of doing this are explanations. I really am a big fan of these for a number of reasons. Let's talk about that. First, what is an explanation? You first have to go, well, what's a typical prediction from your model? Your model is based on a data set, training data. And when you train on that data, when you're finished, you could get predictions from that data. But a typical prediction would be a baseline prediction. A baseline prediction is the middle one. So from every one of the features you included in the model, if you took the middle value and then with all those middle values, fed them and got a prediction back, you call that baseline. Now, what's a middle value? For a numeric value, it's the median, the middle, if you sorted them. You wouldn't want to pick the mean because that could be kind of off-centered by extreme values that are high or low. If it's a categorical variable, you make a little histogram and you pick the tallest bar, and they call that the mode. You pick that one as the middle value and create your prediction. And call that your baseline value. And then when you predict a new transaction, it is different than the baseline, higher or lower. Well, each individual feature has a contribution to that difference. And that's what explanations are. They have feature attributions. Any individual prediction being higher or lower than the baseline gives you information about why that prediction is what it is. Now, why is that important? Well, when you trained on a training set and then you deployed it to an endpoint, a prediction might be based off completely different data that you're monitoring. And you might get a wacky prediction and go, well, why is this? Well, by knowing which feature drove that difference from baseline, You're actually guiding a diagnostic, understanding that prediction. More importantly, like in the world of fraud here, hey, I've predicted something's fraud. Well, it would be great to be able to tell an investigator, whether that's an automated process or a person, hey, this particular instance of fraud is heavily driven by the feature number of transactions in the last hour on that account. That makes it easier to diagnose and interject and act on fraud. Rather than just saying fraud, it's informative fraud now. Maybe you're giving somebody a credit score and it's not what they were expecting. It would be much more informative to tell them the reason your credit score is this is number of accounts open. That's a feature. Well, how do we detect which features drive that is what we're doing with explanations. So let's jump over and take a look at explanations from our model. Now, in this point, we're going to go back to our endpoint, but instead of saying .predict, we're going to say .explain, pass it the same inputs. Now, to get an explanation, you do get a prediction. That's the exact same value we just got. And now the next part I'm going to do is take the explanation part of the response and take pieces of it off and put them in nice print statements in Python to make them easy to read. And when I do that, I see baseline output of 0.5. But this instance's output is 0.949, much higher. That's a big deviance. So what's driving that big deviance? Well, what I'm going to do in this next blob of code is go to the other part of the explanation response that has each feature attribution, each feature and its contribution to the delta here. I'm going to collect those in a data frame and then plot them using a Python package called matplotlib. And when I run this piece, I get this nice chart that very quickly tells me the majority of the difference from that baseline prediction is driven by variable v4. Now, if I knew what v4 was, remember our data set, this is principal components, a redimensionalized version of the data set, but the company that owns the data would know v4 is that thing that I keep kind of mentioning is number of transactions in the last hour. Well, that could drive the diagnostic or the investigation. Well, v14 is also very important. They could bottle that up and say, well, that's interesting. That's the origin of the transaction. They would know to go chase down that part. But they would know they could first prioritize these in their investigation and maybe not worry so much about V17, 25, and 22. And hey, V28 is actually trying to contribute to it being less likely to be fraud. So that's an interesting one. It might be worth looking at as well. These diagnostics are so important to both the use of a model and the understanding of a model. Even understanding the bias of a model, this could lead you in directions to help you do those investigations. I am going to say that's probably the end of our conversation for this. We'll go do one more piece of Q&A and then wrap up. So a good last question. In each of these O2 videos, this is the last one, I talked about, well, why would you use the console and do no code in the first? In the O2B, we talked about why would we use Python clients with interactive code. And in this case, our unique piece of the workflow was bottling up all of this into a pipeline. So let's talk about why we would do that.
Why and when should I use pipelines to create a model with AutoML?
Well, the individual parts of our code, they don't stand alone. Like we created a data set for the purposes of feeding it to a model training facility, in this case, AutoML. And then when that finished building a model, with that asset, we knew we wanted to use it. We could have even put a decision point in our pipeline to look at the confusion matrix and make sure it's good enough. And that's called blessing the model. And then if it passed that blessing, we could then deploy it. In our case, we automatically deployed. Well, by packaging that up, I can do so much more with it. One is I can sit back and relax while it runs. The other is I could start a version of this that automatically retrains. I could be looking at the data coming in using Vertex AI's model monitoring or my own model or my own data monitoring set that says, hey, the training data's distribution of parameters was this. And now we see that new data isn't following the same distribution. That probably means the model's stale. Trigger retraining. I could see that the accuracy of the model, new predictions, well, as I know the truth about the new fraud, if it is or isn't, I might notice that the model is getting worse or maybe even accidentally better. And I go, the model isn't behaving the way it was expected. That's a good chance to retrain it. Well, if I've already bottled it up into this pipeline, it's so easy to just hit run again and get a new one and build decision points into it. If I were building many models at the same time for different types of transactions, well, I could just easily put those into the same pipeline and they could all run in parallel and they could all have their own decision points as they run. Pipelines make this type of automation, these people movers for information and processes, so much easier. Interactive code's great for experimentation and getting the hang of things, but production, this just makes things so much easier to, one, run, but also monitor and recreate. All right, with that, let's wrap today's video up. O2C has been a lot of fun. I'm glad that we've spent some time on AutoML. I look forward to the next series where we're going to do something that's not automatic, but it's still more on the easy side. We're going to use BigQuery. So I encourage you to go to the O3 series. And then as we get to O4 and on, we're going to be doing custom modeling, starting with TensorFlow. I want to say, if you've enjoyed this video, hit the like button. It gives me a pat on the back and lets me know it's worth the effort. If you want more videos like this, hit subscribe. That lets me know people are waiting. And if you click the bell, it'll let me know. It will let you know when I do upload a new one. If you have gotten good information from this, it's great to leave a little short comment below, because that lets others who are watching this video know that it's worth their time. The first thing I do when I see a video this long on YouTube is I look at the top of the comments and make sure it's relevant and useful to what I'm going to watch it for before I spend that time, help others. And then ultimately, the most important thing you can do is, if you notice something I did that needed correcting, or something I could have done better, or if you just triggered a thought about another workflow or a different idea, go to the GitHub repository for this. It's linked in the description if you didn't start there. And click issues at the top of the page and start a new issue. And let's have a conversation about Notebook O2C and those things, that ideas that are triggered. And we can create new content that helps the new viewers long before I can recreate this video. With that, I want to say thank you for your feedback and your time. Let's work together to make the practice of AI and ML more collaborative, accurate, and approachable to a wider and more well-connected audience. Thank you. Have a great day.